Yeah, so once you have configured the system with the number of channels, you have seen the input section. After you configure this instrument and depending on your applications. Now the applications that this instrument can cater is transformer core loss, inverter test, drive test, inverter efficiency, motor efficiency, and so on and so forth. LED test, solar test can also be input. So you can find out efficiency of the solar inverters, you can find out efficiency of the solar panels on that particular given time, or you can connect a system that can simulate a solar array and also feed in and look at the efficiency of the solar inverters. Solar inverters being on a very high scale, a kilowatt and megawatt, can also be fed into this because we have a DC line up to 1500 volts. Now, the 6 channels can be configured in different applications. See, for example, channel 1 can be fed DC and the rest 3 channels can be fed AC, which means the output of the inverter can be connected to the instrument as well as the input of the inverter can be connected as DC. Now, after we do that, the menu here is quite simple and straightforward. So we are right now looking at 3 sections here: measurement, input and system. We also have a file system. These 4 are the basic menus. This instrument employs a touch screen wherein you will be able to have touch screen systems. Here you can configure the wiring pattern. Right now what you see here is a 3-phase 3-wire system where you will be able to have 3 inputs and 3 outputs. And similarly you can have one more system that has 3 separate 3-phase inputs. This is a 2 wattmeter method. We also have something that can go in for a single phase system, which means you can have a 3 input as well as a 2 input and a single input. So you can configure however you want. So currently what we can look at is this. This is a 3-phase system. This is a 3-phase system here. What we are looking at. So we have a 3 input section and we have separate single input systems. Once you configure this, let's assume that you are connecting an inverter. So you give in the DC. So you mention this as DC and say yes. You mention this as a PWM and say yes. So because this is a drive, it's a PWM. Now again, this can be configured either as a 3V3A system or a 3-phase 3-wire system or a 3-phase 4-wire system. Currently we can employ a 3-phase 3-wire system in and DC in and a AC out. Once you have configured this is done, you will be able to see what are the voltage levels, and then you can go in for the channel setting. The channel setting is usually set at mean for PWM. You can have input sections that would give you a phase shift. Now the most important feature of this instrument is that it can employ a phase shift correction. So what is a phase shift correction? Any CT, any clamp that senses current has 2 types of inaccuracies. One is the inaccuracy in the amplitude side, that is what we have to live with. The other is the inaccuracy on the phase shift. So there are phase errors as well as amplitude errors. Amplitude errors are the one that we have to live with because such is the error of this particular, the error of this particular CT here is about 1% because this is a high frequency CT. There are CTs in from Hyoki's offering which can go up to 0.05% accuracy. But the inaccuracies on the phase side, say let it be 0.5 degrees or 1 degree, can be corrected. So phase shift compensation, once you put it on, you can have a phase shift degree compensation. Once that is compensated, you will not have an issue on the phase angle measurement. The phase angle measurement is 100% accurate, and then cos of the phase angle will give you a power factor. Power factor into voltage into current gives you active power. Now that is how we are able to achieve very high instrument accuracy. So coming back to the common section, we have harmonics that can go up to 100 orders. We also have FFTs that can go up to a bandwidth of 1.5 megahertz. This equipment is, like I said, this is an 18-bit instrument with 5 megasample sampling and a bandwidth of DC to 2 megahertz. Okay, so we also have an efficiency section here. Efficiency. This efficiency has an octopus type of arrangement, wherein you can have all your inputs and all your outputs. You have 4 such definitions. You can have a DC-DC converter, you can have a DC-AC converter, you can have a AC-DC inverter, you can have a system setup. So you can have 4 different setup, and you can use all these 4 different for 4 different efficiency, which for instance, you can have a DC in and a DC out, which is for a DC-DC converter. You can have a DC in and a AC out, which is for the drive, and you can have a AC in and the motor out, which is for the motor. And here you can have the system configuration, right from DC to motor. So you can have step-by-step efficiency, and you can have a culminated in efficiency setup also. Similarly, you have a user-defined function. The instrument employs real-time user-defined functions where you could input your formula, and the formulas that you input is automatically taken into account with the existing parameters that it measures, and these parameters are in turn used for calculations such as absolute values or power values of your own methodology. For instance, you can have the LQ and the motor control separate calculation that if you want to. Users can also have their own calculation method. There are 16 parameters that you could, 16 features that you could add up. And last is the motor function. The motor function employs, like I said, your torque, speed, direction and origin. These are the 4 inputs that we discussed on the rear of this instrument. Of these 4 inputs, you can have torque. You can have a torque sensor that gives output of voltage or frequency. You can have an RPM sensor that gives a pulse output. You can have a rotary angle that would give the setup of the position of the sensor. And on the torque side, you can have scale it to Newton meters, kilonewton meters or millinewton meters also. So all you have to do is mention the number of poles and number of pulses for RPM, and then you have the setup of the power. All we have talked now is the setup. Now we can go into measurements. Measurements is, there are few sections here that you could see, starting with the vectors. This is the input vector, this is an output vector. You can scale it however you want. You can have the number of channels that you can see here. Currently we have connected just a single phase system that for you to understand, and thereby we have this single phase system that we have connected here. So we could say this as 50 Hertz AC, and then we come here and measure this lead lag position. So here you could see the voltage and the current position, and this is for the fundamental. Now you can see this is highlighted here. So you can move this to channel 2, the order 2, order 3. You can see here the voltage and the current position of the 3rd order harmonics, and this being the fundamental, and this is the 2nd order, the 3rd order, the 4th order, the 5th order. So that way this is the 7th order, and this is the 11th order. You can see the odd harmonics are huge because the load we are employing is a CFL bulb. So usually it employs a huge amount of harmonics. Before we go into the details of harmonics, let's measure the basics. The basic here, it gives you voltage, current, power, power factor, apparent power, reactive power, phase angle and frequency. Similarly for voltage, you can get URMS, that is VRMS, V mean, V fundamental, V THD, the total harmonics distortion, V peak on the positive and negative side, and if there is any DC component, and this is a pure AC component, and this is the frequency of the voltage. Similar parameters for current. Now this is a single phase system. Let me show you a 3-phase system here. The 3-phase system employs more features for you to see. As you see, there are 3-phase systems here. it employs 3 voltages, 3 currents and sigma voltage, and similarly 3 voltage, 3 current and sigma current. And on the power side, you could see that it employs total power as the total apparent power and total. This is a very good calculation where you have different types of power factor, and the total power factor is assumed to be a calculation of these 3. Now, we also have a waveform. This is a voltage waveform. In yellow, this is a current waveform in green. So we could employ this current waveform and voltage waveform. You could see that right here. What you see in the bottom is the FFT. This FFT you could put your cursors and measure, and I can give you FFT bandwidth of up to 1.5 megahertz. So I can employ FFT on frequencies of 50 Hertz fundamental, say. At 50 Hertz fundamental, I can give you a frequency calculation and a FFT calculation of every 5 Hertz, which means I can give you a harmonic of every 5 Hertz interval, which is pretty amazing for an engineer to calculate on issues on harmonics. So which means right from 0.1 Hertz to 1.5 megahertz I can give you harmonics at 5 Hertz resolution. Okay, so once you get this setup done, you'll be able to configure this resolution bandwidth and make a table out of it and get what needs to be done. So similarly, these are the harmonic orders as well as the list. You get both graphical display as well as the list display. You have a plot of trend. So you can have a trend plot, XY plot of say frequency versus current, frequency versus RPM, frequency versus torque, current versus torque, you can have any types. And you have about 8 parameters that you can plot as a trend. You can plot XY or trend. This is quite useful when you are looking at certain controls of motor, if you would like to employ such things. So on the measurement side, you have the stage by stage. You can see here it is channel 1, 2, 3, 4, 5, 6. So these are channels on the instrument, and this is the motor. So you have torque, speed, power of the motor and slip. So these are the 4 parameters that you can get in the motor measurements. Then you can directly shift to the efficiency. The efficiency here, you get an efficiency like I discussed in terms of percentage or absolute values, however you want to look at. All these can be saved on to the media, and this also employs output, like I said, the raw output of the waveform. It can be connected to an oscilloscope, or it can be connected to a data logger, or it can be connected to a recorder for long-term measurements, long-term acquisition. And finally, all these data that the power analyzer acquires can be saved in either ASCII format or a CSV format that can be analyzed separately by a separate tool, either on a MATLAB or the tool that we have, or a third-party tool, for you to analyze all voltage, current and efficiency waveforms. Thank you.